Hi guys, welcome back. We have now laid the foundation to talk about functions. We're going to look at what is meant by the term function. We're going to look at domain, range, define a lot of terminology, and see then how functions are even applied. So let's get into it and start by looking at maybe a motivation example here. Okay, so we've got our number systems. We want to discuss how the relationships can be established between sets of numbers. And that relationship is really what a function defines. So here's a little motivation problem. A car rental company charges customers a service fee of $50 plus $60 per day for a maximum of 15 days. Your job is to write a rule that tells employees how much to charge based on the number of days the car is rented. Your work will require you to write two sets of numbers. The first set would be the number of possible rental days, and the second, the number of possible amounts to charge. Then we need a rule that assigns to each of those sets. So let's start with the number of possible days of rental. Okay. So, you rent a car, could be rented for 1 day, could be rented for 2 days, 3 days, 4 days, 5 days, 6 days, 7, 8, 9, 10, 11, 12, 13, 14, or 15, okay? Right, we're told a maximum of 15 days. Notice that in this set of numbers, we don't have any, no, these numbers are all natural numbers, right? You're renting for whole numbers of days, not half a day, not a quarter of a day. And so natural numbers from 1 to 15. And then this other set is the charge, the rental charge. Okay. Well, for 1 day, the rental charge would be the $50 plus the 60 per day. So 50 plus 60 is 110. For 2 days, you've got the $50 service charge plus the $60 for 2 days. So 60 times 2 is 120. Here you'll have 170. So go ahead and fill out this chart. Go all the way down. You might want to pause it, but I want to know what all the possible rental charges are. Okay, so go ahead and pause and do that. Okay, hopefully you've paused, and hopefully your numbers, whoops, look something like this. After 170, we're essentially going to add 60 to that, right? And get 230 and 290 and 350, 410, 470, 530, 590, 650. Oh, whoops. Sorry, didn't mean to zoom out here. 50. Sorry, I lost my place here. Let me see. 7, 60, 60, 60. Okay, then 710, 770, 830, 890, or finally 950. I'm sorry those are so small, but you get the idea. Now we need a rule. And here's where some algebra comes in. If you got these numbers here, then you were probably already thinking in terms of a rule. You'll notice that we can articulate this verbally, right? The $50 plus the $60 per day. Maybe I'll call that D. And then this will be, I don't know, rental charge. So C for charge, let's say. And I'm going to add something to this C. I'm not just going to leave it as C. I'm going to write this in what's called function notation. The name of the function is C, and the value of C depends on D, the number of days, which makes sense intuitively, right? The longer you rent the car, the more you're going to pay. The amount that you pay is dependent on how long you have the car. That's what this notation here captures. It does not mean C times D. It means C is determined by the value of D. Well, what are the allowed values of D? Well, that's this column. And based on those, what are the allowed values of C? Or maybe I should say the only possible values of C. Well, that's this column, okay? So we have a relationship that we've established between the number of days and the charge. Now, it might be worth noting too, because remember, this function is defined only for certain numbers. So I could define it this way, where D equals 1, 2, oh, I can't write, I'm sorry, 1, 2, 3, dot, 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 all the way up to 15, okay? All right. So here's some definitions. A relation is a rule that assigns members of one set with members of another. The first set is called the domain, and the second is called the range. In other words, you got a set of numbers on one side, a set of numbers on the other, and you're just matching them up. That's a relation. A function is a relation such that each domain element is paired with one and only one range element. In other words, if this is my domain, and this is my range, D and R, D for domain, R for range, then, whoops. With a function, I might have, I don't know, say 1, 2, 3, 4. Maybe I've got 1, 8, 9, 0. Maybe 1 gets sent to 8, 2 gets sent to 0, 3 gets sent to 1, and 4 gets sent to 9. Notice that there's no ambiguity between domain and range. Each of these domain elements is going to exactly one range element. This would be a function. If, on the other hand, my domain, whoops, or 1, 2, 3, 4, I don't know, my range was 1, 4, 0, 3, and I had 1 going to 1, 2 to 4, 3 going to 0, and 3 going to 3, maybe, I don't know, maybe 4 goes up here to 1. Then notice that we have failed that condition of the definition, right? 3 gets sent to 0 and it gets sent to 3. So not a function, okay? Also, notice it's okay if the range element is the same for two different domain elements, right? 1 went to 1, 4 went to 1, but you can't have one input going to two different outputs, okay? Again, going back to that soda machine I mentioned in the first lecture, right? If you pressed the button for a soda and you had, and out came the soda and something else, as nice as that may be, the machine is broken, right? It's no longer functioning properly. You should only have one output when you give the function an input. All right. Let's keep going here. So here's some examples. And again, you might want to pause this and work through these before you see me do them. So this would be a good time to pause. If not, you can always go back, but let's see. Decide if the set of ordered pairs represents a function. Well, the first thing you should know is that typically when you represent a function in ordered pairs, the the x coordinate is the domain element, and the y coordinate is the range element. So I could say, okay, I could look at the domain here and say, okay, the domain is 2, 4, 0, 3, 1, right? I'm just looking at these first values. The range is 3, -1, 9, 3, and -2, the y coordinates, right? 3, -1, 9, 3, and -2. Well, 2 goes to 3, 4 goes to -1, 0 goes to 9, 3 goes to 3, 1 goes to -2. Do we have any domain elements getting sent to different places? No, we don't. And so this is a function. Okay. How about this next one? Well, my domain, I've got 1, 2, 5, and 9. My range, I have 7, 7, 7, 7. Wow. Or maybe I can just say I've got one range element, 7. 1 goes to 7, 2 goes to 7, 5 goes to 7, 9 goes to 7. Oh, goodness. It's a lot of inputs. It's only one output. Same output, I should say. Well, this is a function. Because again, the definition says you can't have an input going to two separate outputs. It says nothing about an output having more than one input, okay? And so this is a function. How about C? We've got domain elements 3, 2, 3, 0. So I don't need to repeat 3 if I've already got it in my set. And my range 8, 4, 9, and 1. So we have 3 going to 8, 2 going to 4, 3 going to 9, and 0 going to 1. So 3 gets sent to 8 and 9. So this is not a function, okay? And you know, this, you may in a past studies heard of the vertical line test. When you have a graph of a function, which these ordered pairs naturally suggest, right? You see ordered pairs, you're probably tempted to graph them, right? The first two examples, right, had no single x value going to two different y values. So really, whatever your function might look like, right, any vertical line that you draw through it will only cross the function in one place. In other words, this input has one output. This input has one output. Input to output, input to output, and so on. Whereas if you did not have a function, then you might have something like, I don't know, let's be ridiculous, something like that. So here, there are places where one input gives you one output, but that's not true everywhere, right? Say here, right? Here's my input, but it actually goes with two different outputs. And so we would say that fails the vertical line test, and therefore that does not represent a function. If you're looking at example C here, you might have this situation, right? 1, 2, 3, 4, 5, 6, 7, 8, and then we'll go all the way. And then 9, and then 1, 2, 3. Right, we had 0 and 1. We had 2 and 4. Then we had 3 and 8 and 9. So you can see that, right? Blow those points up a little bit. 3, 8, 9. The vertical line test has failed. Okay. Okay, here's a nice analogy. I've mentioned it already, but I like thinking about functions as machines. And so maybe we'll start simple. Let's say we have this machine. F of x equals x squared, I don't know, plus 3. And so this machine, if you were plugging in values, like if I said, okay, oh, I'm sorry, let me rewind. Notice the function notation, right? This is pronounced f of x. The name of the function is f. The inputs are x, okay? Now, if I asked you to input, I don't know, say 2, your brain would probably do something like this. 2 squared is 4, plus 3 is 7. Well, think of it this way. You have x's going into this machine. And the first thing that this machine does is square. After squaring, the machine then does what? It adds 3. And then, whoops, got to get out of the machine. What comes out, we would call f of x, okay? So example, if I plugged, I don't know, 5 in, I put 5 into that machine, it would come into the first chamber, it would get squared. And so 25 then, would be coming in to the next chamber, and you could have 23 or 25 plus 3, and you'd get 28, okay? So you can think of them as machines, all right? And now to look ahead a little bit, under certain conditions, we can rewind this machine and figure out what input went with a certain output, but there needs to be a little more restrictions on the function for that to be possible. So how do we represent functions? Well, there's really four ways. One is verbal. Can we just describe what's going on in words? The $50 service fee plus $60 per day is the amount of the rental charge. Tabular, in other words, a table. Can I look for the rental charge, can I look for the number of days and then scroll over and see what the rental charge should be? That's tabular. Algebraic, give me a rule involving variables, numbers, and operations, right? That was our C of D equals 50 plus 60D. And then graphical, or just with ordered pairs, right? Can we plot these? And those are the 4 main representations of a function, okay? And so if we look at this next example, we could really talk about these 4 representations within that context. And so the verbal, remember well, let me rewrite it here. So the car rental is $50 plus $60 per day, okay? That would be verbal. Well, tabular, we'd have the days, and we'd have the charge. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then 110, 170, 230, 290. Again, I'm just adding 60 every time. 410, 470, 530, 590, 650, 710, 770, 830, 890, and 950. This would be tabular. Well, the algebraic expression would be that C of D equals 50 plus 60D. Okay, that's algebraic. And then if I wrote the set of ordered pairs, 1, 110, 2, 170, and yes, I'm not listing them all because you get the point. But I could list those ordered pairs and then graph them. That would be a graphical representation, okay? So finally, we hinted at this already, but when we think about a definition, considering the definition of function, what common feature will the graphs of any functions possess? Keep in mind that the ordered pairs are going to have the format input, comma, output. And for a function, for a function, we have that each input has only one output, okay? So input, output, ordered pairs, your brain should immediately be thinking graphs, right? You're hopefully seeing the XY coordinate plane and you're thinking, okay, I can graph my inputs on the x-axis, my outputs are the y, I can form these points. Well, if each input has only one output, you're essentially saying each x value has only one y value to go with it. And you get what's known as the vertical line test, which we talked about before. Passes the vertical line test. Any vertical line will only cross the graph in one place because that one place, remember that location on the graph, that's the output, the y value, right? Only goes with that single x value, okay? So if you have a function, if you have a graph of some relation and it passes the vertical line test, namely any vertical line only intersects the graph in one place, then you have a function. All right, so that's our discussion of functions. What were the big ideas? Well, you can think of a function as a machine. When you talk about a function, you always need to know what the domain is. What values are you allowed to plug in? With our motivation problem, talking about the car rental, right? No one would ever plug in 2.5 to that equation. It doesn't make sense the way the function is defined. So you have some rule, maybe an algebraic representation of the function, but that rule needs to be accompanied by a description of what you're allowed to input. What else did we talk about? Yeah, the vocabulary, right? All inputs, that's known as the domain. Set of all outputs is the range. If you want to look at a graph and decide if it represents a function, it must pass the vertical line test. At the end of the day, functions are just a specific example of that broader term, a relation. But really, we're going to be studying functions. Functions, different classes of functions form much of what we do in pre-calculus and calculus as well. So as we move forward, I always want you having in your mind when you're dealing with a function, what is its domain and what do you expect its outputs to look like, okay? So with that, you need to definitely try some problems, work them out. The more practice, the better. And when we come back together, we will start talking specifically about the graphs of functions and how they are transformed. So, as always, until then, happy studies.